Welcome to 6.2 video lesson, Algebra 2. The concept is multiplying and dividing radical expressions, and there are 9 boxes. This is a big lesson, so you need some cookies and some tea or some milk or something right now, so make sure you've got some snacks, okay? Let's dive right into box number 1. The first property that we're going to talk about here is the products, and it says if the nth root of a and the nth root of b are real numbers, then when I multiply them, it's just the same thing as the nth root of the giant AB underneath the radical. I think you intuitively know this, so let's talk about this. So I have 3 examples here. The first 2 are going to work, and the third one is not, and let's talk about why. So the cube root of 2 times the cube root of 7, that can be the cube root of 2 times 7, or the cube root of 14. We can do that. We're allowed to do that because my indexes match. I'm good to go. This next example, the 5th root of 5 times the 5th root of 2, I am allowed to keep going and saying this is the 5th root of 10 because the 5 times 2 gives me the 10 as long as my indexes match. Take a look at example, this one with the red box to it. The cube root of 6 and the square root of 2. Ain't gonna work. I cannot multiply those together because the indexes do not match. So that's our first basic property in box 1. Okay, here's box 2. Let's do this example together. It says the cube root of negative 4 multiplied by the cube root of 2. Well, I am allowed to keep going because my indexes match. So this is the cube root of negative 4 times 2. That is the cube root of negative 8. And this, in the last lesson, means what number times itself 3 times is going to give me back negative 8. And we have learned that that's negative 2. So therefore, this is a value of negative 2. So this whole thing is equal to negative 2. So we have multiplied and simplified. Okay, box 3, a U try. Multiply radical negative 5 times the 5th root of negative 5 times the 5th root of negative 2. Ready, set, go. Okay, hopefully got the right answer with a 5th root of positive 10. The reason we can keep going is because we have like indexes. So it's the 5th root of negative 5 times the negative 2, which gives us the 5th root of positive 10. Okay, box number 4 is an example. We're going to reduce the radical to simplest form. Simplest form just means as much as possible. Okay, so here is the idea. I'll do this in blue. The square root of 24 means that I am looking for the largest perfect square that's a factor of 24. So this is equal to, how about an 8 times a 3? Okay, that is true, that's 24, but neither one of those is a perfect square. So let's try something different. What if I did 6 times 4? Well, that's also 24, and 4 is a perfect square, and it is the largest perfect square that's a factor of 24. So if you want to start the problem by listing all the factors of 24, you could say, well, there's 1, 2, 3, 4, 6, 8, 12, and then 24. And then ask yourself, which one's the largest square, perfect square? That would be 6. It would be 4. So that's the one I'm going to use. So this can be broken up into the square root of 6 multiplied by the square root of 4. That, of course, is the number 2. So I'm getting 2 radical 6. So the simplest form for the square root of 24 is 2 radical 6. Let's do the same thing with the cube root of 24. So now, instead of the largest perfect square, I'm looking for the largest perfect cube. And I know that 8 is a cube, so I'm going to go ahead and go with that first one that we did, which is rad 8 times rad 3, which is radical 8 times the cube root of radical 8 times the cube root of radical 3. Now, this is a perfect cube. This is the cube root of 2 cubed times the cube root of 3. And the cube root of 2 cubed, which we have learned, is just going to give me back 2. So I have 2 times the cube root of 3, and that is the most simplest form for the cube root of 24. So again, you're looking for the largest index that's a factor of the number underneath the radical sign, or the radicand. Okay, box 5, this is an example. We're going to simplify and put this expression into simplest form. Now, this could be daunting for a lot of students, so I want to give you a strategy on how to go about it. I'm looking for the cube root of 54x to the 5th power. Okay, so the first thing I want to do is I want to break this up into the cube root of 54 multiplied by the cube root of x to the 5th. I'm going to deal with each of these separately. So first, I need to figure out how to break down the cube root of 54. And a lot of students struggle with this. So here's what we're going to do. We're going to write down all the factors of 54. So we got 1, we got 2, we got 3, we got 6, we got 9, we've got 18, we've got 27, and we've got 54. So 1, 2, 3, 6, 9, 18, 27, 54. Okay, cool. Now that we know that, which of these is the largest perfect cube? That's the one that we're looking for. Which one is the largest perfect cube? Well, 1, no, 2, no, 3, no, 6, no, 9. Yeah, maybe, right? Okay. 18, 27. Nope. 3 times 3 is 9. 9 times 3, 27. Oh, maybe 27. 54. So we're looking for the largest perfect cube in this, right? Is 9 a perfect cube? No, 9 is a perfect square. So that wouldn't work out. So 27. That's the one that we want. Okay. So this is going to break it down to... We're going to break this down to the cube root of 27 times 2. Why am I doing that? Because 27 is the largest perfect cube. Because I can write this as the cube root of 3 cubed times 2. 3 times 3 is 9 times 3 is 27. That's good news for us because this is going to break down into the cube root of 3 cubed times the cube root of 2. Now this, of course, is just the number 3. And this I cannot simplify anymore. So now all I have to do is deal with this part. Now this can be broken down to the cube root of x to the 3rd times x squared. Because when we multiply our exponents, we add them together, and 3 plus 2 makes 5. Now why did I choose that? Because for the same reason, this is going to be the cube root of x to the 3rd times the cube root of x squared. This, of course, is going to give me x back, and this, of course, I can't do anything with, the cube root of x squared, because my index is larger than my exponent. So when I put this all together, look what I have. I have a 3, so I'll write down a 3. I have an x, I'll write down an x, and then I have a cube root of 2x squared. And that's what we end up with. Oh no, Microsoft just quit on me. Okay, so anyways, back up. I got a 3, so I'm going to write down my 3. Oh shoot, okay, the videos, they recovered in the wrong spot. Okay, so this is going to let me redo this for you. X to the 3rd times the cube root of x squared. So the cube root of x to the 3rd just gives me back my x, and then the cube root of x squared I can't do anything with. So I have a 3, I have an x, I have a cube root of 2x squared, and that is my simplest form of this one right here. Okay, right now try your best to break down and simplify the cube root of 128x to the 7th. Okay, let me walk you through this one again. So, we're going to start by saying separating the numbers and the variables. So I've got the cube root of 128 times the cube root of x to the 7th. Let's find the largest perfect cube from this list of all factors of 128. Hopefully you realize it's the number 64, because that's 4 to the 3rd. So here we go. So I can rewrite this as the cube root of 64 times 2. That's going to be the cube root of 4 to the 3rd times the cube root of 2. This is just the number 4, and I still have a cube root of 2. That takes care of that part. Now, I'm going to break this down to the cube root of x to the 3rd times x to the 3rd times an x to the 1st. Because remember, when we multiply our like bases, we add the exponents. 3 and 3 makes 6, and 1 makes 7. This breaks down to the cube root of x to the 3rd times the cube root of x to the 3rd times the cube root of x. This, of course, is just the number x. This, of course, is just the number x. And this is a cube root of x. So therefore, when I put this all together, I have a 4 That's that guy. I have an x squared. That's these two, because x times x is x squared. And I have the cube roots of 2x. I know that this is challenging, and we will practice more in class, but I want to give you the general structure and strategy on how to do it. Okay, box 7, here's a big property. If the nth root of a and nth root of b are real numbers, and as long as b is not the number 0, then if we are dividing the same nth roots, we are allowed to combine them into a single nth root. So let me give you an example. If I have the square root of 12 divided by the square root of 2, since they have the same index of 2, I can say this is the square root of 12 over 2, or the square root of 6. I'm allowed to do that. That's what this illustrates of this property right here. Okay, in box 8, we're going to rationalize the denominator using square roots. So I have 3 examples here for you. So here is the idea. We're not allowed to keep an expression with a square root in the bottom. So what we're going to do is we're going to multiply by the thing that cancels out that root. So as an example here, the first one here, if I multiply the top and the bottom by the square root of 2 and the square root of 2, well, first of all, you should realize that this is just no more than a fancy 1. So I'm not changing the value of the expression, so I have not broken any rules. And furthermore, you should notice that the square root of 2 times the square root of 2 gives me back the square root of 2 squared. And if my index and my exponent match, then I just get back the number 2. So this is going to give me the square root of 2x all divided by 2. And there is the same equivalent expression, except I no longer have a rational or a root in the denominator. Now, the second example is a little bit more tricky because notice I have a cubed root. So what I want to do is I want to ask myself, okay, what number or what can I multiply top and bottom by so that I end up with something with a cube root of 2 to the third? Well, that would be the cube root of 2 squared. Why is this true? Because look at the bottom. The cube root of 2 times 2 squared gives me the cube root of 2 to the third, which just gives me back the 2. So I multiply top and bottom by the cube root of 4. And then when I simplify this, I'm going to get the cube root of 4x all divided by the number 2. Okay, so that's the rationalized denominator version of that one. The third example I have for you, the first step would be to, first of all, break this up into the cube root of 5 all divided by the cube root of 3x. So again, ask yourself, what can I multiply by to give me back the cube root of 3x to the third? Well, that would have to be the cube root of 3x quantity squared. So multiply by top and bottom by the cube root of 3x quantity squared. Why is this true? Because look, when you multiply the 3x times the 3x squared, you get 3x to the third. So on the top, I'm going to get the cube root of 5 times the cube root of 9x squared, all divided by 3x. I can take this one step further and give me the cube root of 45x squared all over 3x. And again, I know where this is challenging, but we are going to practice in class. I just want you to see it ahead of time. And the last box is a you try. Go ahead and try to rationalize this denominator. Okay, so I multiplied top and bottom by the 4th root of 5 cubed, because when I multiply the 4th root of 5 cubed times the 4th root of 5, I get the 4th root of 5 to the 4th, and that cancels out. So therefore, when I keep multiplying all this out, 5 cubed is the 125. I get the 4th root of 250 over 5. Okay, big lesson. Nice job. Way to hang in there.